Us to concentration and rate laws. This, I can't remember if this is actually section 14.3 or they renumbered these ones and it got confusing for me. Okay. So as we saw, in general, higher concentration of reactants, the faster the rate. More collisions can happen, reactions take place quicker. And so what we're going to do, because we don't want products to build up, is determine the reaction rate at the beginning of the reaction before products can build up, and we're going to use what we call starting conditions. Okay. Let me see. All right. So what we're going to do is we're going to use experimental data to write a rate law expression. And rate law expressions have a general form, and they start with the word rate. Rate is equal to a rate constant, which I write as, and you will see as lowercase k. I usually write this in cursive because we're going to use uppercase k in the next chapter, and this slightly decreases the confusion. Rate equals the rate constant k times the concentration of reactants raised to a power, not a stoichiometric coefficient. We're going to refer to these as orders. Okay, so let me write a couple things here. K is the rate constant. M and N, it's important to note these are not always, because sometimes they are, stoichiometric coefficients. So what we're going to do is use starting conditions of a reaction to determine what M and N are. And these are referred to as orders. So a reaction has first order with respect to A or second order with respect to A. And basically what this is doing is just a power. Okay, we're raising the concentration to some power, usually 1 or 2, sometimes 1/2. Okay. And it is telling us how the rate is dependent on the concentration of that reactant. So that's all it's doing. We're just trying to figure out what concentration does to the rate. Okay. So for the reaction of ClO2 plus OH minus is hydroxide to form products, we could write out a rate law like this. Rate equals the rate constant times ClO2 raised to the power of M times OH minus raised to the power of N. Okay, and this rate is the exact same rate that we saw in the previous slides. So numerically it's the same thing. But now we're just using a different technique to figure out this rate law expression, which is this portion of the equation. Okay, so as I mentioned, we're going to use the method of initial rates. And so when you get a problem like this, you will often see a table that has an experiment number and concentrations of both reactants and a value for an initial rate, usually in moles per liter per second. Okay. And so we're going to use these data to calculate M and N. Now, essentially what we're going to do is hold one concentration of reactant, one reactant's concentration, hold it constant, and change the other, and see how the rate is affected. Okay? So for instance, in this problem, in experiments 2 and 3, the concentration of ClO2 is constant, 0.02 moles per liter. The concentration of hydroxide is tripled, going from experiment 2 to experiment 3. And so our task is to figure out what happens to the rate. Okay. Is it doubled? Is it tripled? Is it halved? Is it the same? Okay. Those are generally the options. There's, how do I want to do this? Okay. Oh, I'm on the next slide already. So to determine M, the order with respect to ClO2, we're going to use experiments 2 and 3. To determine N, the order with respect to OH minus, we're going to use experiments 1 and 2, because there, the hydroxide concentration, oh, I did it backwards, sorry. Nope. Erase, everyone erase. The one that you're holding constant is not the one you're determining the order from. Okay, so the one that's changing is the one you're determining the order for. Sorry. Okay, so determine M is ClO2. We change the concentration of ClO2 in experiments 1 and 2, hold hydroxide constant. Okay, so those we can use to determine how the rate is affected by the concentration of ClO2. When we hold ClO2 constant, we can then look at how the rate of OH minus, how the rate of the reaction changes with the concentration of OH minus. So we'll use 2 and 3 to determine N. Sorry, I know I said that backwards, so that was probably confusing. Questions? Okay. There is a way to mathematically do this, but before we get to that, I want to look at this very generic, but works most of the time method. Okay? So let's say we double the concentration of a reactant, the other one stays constant, and then we look at what happens to the rate. These are usually the options. It's halved, it stays the same, it's doubled, it's quadrupled. We can then use that information to predict the order, to predict that last column of data. So if we double the concentration of reactant and the rate doubles, that means that the order is 1. If we double the concentration of reactant and the rate is quadrupled, the order is 2. All right? And the reason being is that we are looking at something raised to a power. Okay? I'm going to write this. If we have a concentration of some reactant, and we raise it to its power, its order, what is the rate? Okay? Essentially what we're doing here, this is what we're doing, we're solving for M. So if we say that if we double the concentration, we're going to put a 2 in here, the rate is quadrupled, 4, if both of those were 1 and 1. Okay. What does M have to be? 2, right? 2 to the 2 equals 4. So if the rate, if we double the concentration, and the rate stays the same, what's m? 1. This is what we're doing. And this is what, n or m, whatever I did. This is why I like the table. You know, this is like you're finding orders, you're basically figuring out that exponent. This is the way to think about it in terms of less mathy, if you like that approach. Okay? Yeah. It is not 0. Oh, what did I say? Did I say stays the same on the second one? I said, okay. Rate, the concentration is doubled, the rate is doubled, m is 1. Did I say stays the same? I apologize. Yeah, okay. Now, these ideas. Okay, wait, before you leave. This equation is the other way to do this, all right? This is the same exact thing that we're doing, but this is not on the exam. But if you're struggling with figuring out those rates, sort of doing that mental math or figuring out the power, this is one way to solve for these. And it's relatively easy if you wanted to memorize it. You could do that. The rate law is given by an equation, rate equals the rate constant K times the concentration of the reactants raised to some order. Okay? And I've given you a few ways of determining the order. There's one that, and again, you're not going to get this equation, but you can determine the rates, the orders by looking at the rates and the concentrations. There's another equation that I think is better. I posted a link in Carmen to an online textbook that does a great job of explaining this equation. And so I think we should finish up this problem, figuring out m and n using this method. Okay. So we need to determine the order with respect to ClO2. Okay, so that's our m. To do that, we're going to use some experimental data, and that experimental data, we're going to change the concentration of ClO2 and hold the concentration of the other reactant constant. So in experiments 1 and 2, we change the concentration of ClO2, but we hold the concentration of hydroxide constant. And we can look at how the rates change. Okay? So for ClO2, and we're just going to, when we assign initial rate 1 and initial rate 2, we're going to take the bigger number over the smaller number, okay? Just to make these positive, although it doesn't really matter, but positive numbers everyone appreciates, I think. So we're going to take experiment 1, and we're going to call that our initial rate in the numerator, 0.0248. And then divided by this other rate, 0.00276, equal to the concentration for that first one, 0.060, over the concentration for the second experiment, 0.020, raised to some power m. Everyone see how we're doing that? Okay. So when we divide these out, we end up with something close to 9, right? No. I forgot a 0. Oh, no, it's there. Let me go to my notes so I'm not talking without thinking. Sorry. Okay. CO2. Oh, okay. All right, what do we get when we divide 0.0248 by 0.00276? Anyone do it? Is it close to 9? What'd you get? 8.98. That's what I wanted to know. Because it is not exactly 9, but it is close enough to 9 that we're going to call it 9, okay? So we're going to say 9 equals 3 to the m. And what does that make m? 2, okay? Okay, everyone okay with that? Yes? Yes, so the 3 came from dividing the 0.06 by 0.02. That one I was able to do in my head. Yeah. So this is basically this exponent, okay? And so what that exponent is telling us is how the reaction proceeds with respect to the concentration of that reactant. So what this is really telling us is that if we triple the concentration of ClO2, the rate goes up 9-fold. Okay, so it's highly dependent. The rate is highly dependent on the concentration of that. Okay. That makes sense? Are we okay if I skip doing N and I write the answer? Go through and let me know if we can talk about it more on Wednesday if you want to go through another one of these problems. But in this one, you'll use experiments 2 and 3. Use these concentrations, use these rates, and see what you get, okay? Yeah?
Does it matter what experiment you use?
It does matter which experiments you use, yes. Actually, let's... This one useful? Yeah?
So if you use that bottom equation, would it automatically just give you 2?
Yes. Yeah. Anything else? Okay. One we haven't done, okay? Just a little clean it up a little bit. So again, when we're doing these experiments, the way we design them is that we want to change only one thing at a time. And so by only changing, in this example, the concentration of NO and leaving the concentration of H2 constant, we can see how the rate is affected by changing that concentration of NO. So that's what you're looking for in the table. So basically look at the pairs that you can make. Here in 1 and 3, the concentration of hydrogen is constant and the concentration of NO is doubled. So we can use experiments 1 and 3 to determine the order of NO. Determine order with respect to the concentration of NO. And then for the concentration of H2, we're going to hold the NO concentration constant and only change the H2. Okay? So there we can use experiments 1 and 2, determine the order with respect to H2. Yeah. Does that make sense? Do y'all like the... Okay, so let's do this problem actually because we do something different here. So we are going to determine the rate law expression, which is rate equals the rate constant K times the concentration of NO with respect, or to raise to some order, times the concentration of H2 raised to an order. So that we're going to need to determine M and N to determine the rate law expression. And then we're also going to determine the rate constant, so determine the value of K. So that's another thing you can do with these problems. And we'll talk about what K means here shortly. But let's do the math and figure this out. Okay, so using that equation we saw in the previous slide, we're going to let's determine the order with respect to NO and take experiments 1 and 3. Okay. And we'll do rate divided by rate. 4.92 times 10 to the minus 3 over 1.23 times 10 to the minus 3 equals concentration over concentration raised to some power. 0.02 over not a 0.02. 0.2 divided by 0.1. Okay. So we end up with something close to 4 on the left-hand side equals 2 to the m. So what does that make m? Yeah. So m must be 2. 2 to the 2 is 4. And then for H2, we're going to use experiments 1 and 2. We'll do 2.46 times 10 to the minus 3 divided by 1.23 times 10 to the minus 3 equals, so that's from here and here, 0.2 divided by 0.1 raised to some power. We'll call that one n. Everyone okay with where I'm getting those data? And so we'll end up with 2 equals 2 to the n. And what does that make n? 1. Very good. So then the rate law expression is rate equals K times concentration of NO squared times the concentration of H2 raised to the first, and we'll just leave that off. Everyone okay with that? Yeah.
So the coefficients, like, not really matter.
The coefficients do not necessarily matter. Yeah, stoichiometry does not matter for these types of problems. Yeah. Yeah.
If we just ask them to the rate law expression and not putting a constant, we don't need to solve for K when it's fitting to the expression, right?
Correct. So if you just need the rate law expression, you do not need to solve for K, only if it's explicitly stated that you need K.
When we were solving for n, could you do like, 4.92, like 2.46 divided by 4.92, since it has the same,
Oh,
since it's 0.1 as well? You know,
you're looking at experiments 2 and 3.
one, or for like solving for n.
Solving for n, so that's
Yeah.
H2. Well, no, because you couldn't use 2 and 3 to solve for the order with respect to H2 because the concentration of NO is also changing there. So we're changing 2 things in those. Yeah, so that's a good question. Anything else? Okay, cool. Yes, please know how to do these. Okay, so then solving for K. This is actually pretty straightforward because now that we have the rate law expression, we can take any of the experiments, 1, 2, or 3, plug in the values for concentration and for the rate, and calculate our rate constant. So which experiment do you want to use? 1, 2, or 3? 3, I heard a 3. Okay, great. So we can use any experiment, but in this case we'll use 3. And we're going to plug in the values into our rate constant expression. So our rate for experiment 3 is 4.92 times 10 to the minus 3 equals some constant K times the concentration of NO, which is 0.2, and that's squared, times the concentration of 0.1, and that's raised to the first. Okay. And so we can rearrange, multiply, divide, square some things, solve for K, and what do we get? 1.23, I believe. Feel free to check me on that. I use a different experiment in my notes, so yeah.
Remember we're running them out, do we put parentheses or brackets around the number?
If you're writing it out here, brackets or parentheses, it doesn't really matter. I leave the brackets just so I remember its concentration. But there's always a good chance I'll slip up and put a parentheses. Either one's fine. Yep. Okay, but K also has units. So this is actually the harder part, is figuring out the units. All right. Okay, so, whoops. What are the units on the rate constant? So we essentially do a unit analysis, which basically just means plug the units in instead of values. So for rate, we have moles per liter minus 1. Oh no, sorry. I see what they did. For rate, we have moles per liter times second to the minus 1. So that's coming from here. Moles per liter times seconds to the minus 1, which is also moles per liter over seconds. I'll leave it like that. Equals K times moles per liter squared times moles per liter. Okay. Probably was smarter to rearrange and solve for K first, but I don't always do the smartest thing. So if we, so when I would divide this out, moles per liter times seconds to the minus 1, divided by moles per liter squared times moles per liter. I'm going to cancel out one set of moles per liter, and I'm left with seconds to the minus 1 over moles per liter squared. Okay. Units on the rate constant K can be wacky, right? This is a little wacky, right? I like thinking about what that unit means is really challenging. But that is the unit on the rate constant. Okay? And it's going to be different because it's going to depend on the order. The other term that you're going to see is overall order. And this is just the sum of the orders for the reactants. So for this rate law, we had second order with respect to NO, and first order with respect to H2. And so the overall order is 3. Okay? Sometimes I think there might be a couple homework problems where you're given the overall order and you're asked to find another one. Okay. Questions on that? I am going to fill in this problem later, okay? In this problem, it's actually the same continuation of the previous slide where we figured out the rate law expression for this reaction with NO and H2. But then we essentially can determine the rate and then relate the rate for the reaction to each of the reactants and the products. Okay, that goes back to section 14.2, I believe, or one of the early ones. Okay, I'll fill that in later. And then just sort of to summarize here a few things. Rate law expression, okay, rate equals K times the reactant raised to an order times reactant 2 raised to an order. And what does the rate constant K mean? If we have a large value for the rate constant, it means that that reaction occurs very quickly. And if it's small, the reaction is slower. Okay. You can solve for K. We just did that. If you know the rate law expression and some other data points. Exponents are the reaction orders with respect to each reactant, and the sum of the exponents is the overall reaction order. All right. Questions on any of that? Okay. This is another example I'm going to skip for now. So this one we're going to write the rate law expression, which is this stuff we're learning in this section, 14.3, and then look at how the concentration changes with respect to time, and that's our earlier section. I'll fill that in, and you can check your work there. And then this is one more example. Again, I'm going to fill this in later. This is, I like this problem because you have 5 experiments to choose from. Okay, so you can pick which ones make the most sense to determine the orders with respect to BF3 and NH3. Okay, gives you some options for rate law on to determine the overall order for the reaction, and then calculating the rate constant. Okay. Like I said, fill that in. I'll fill that in. All right, so let's go on.